This section covers correlation and regression. So although we are still looking at relationships between variables, but unlike the chi-square test, what we're going to look into this one are relationships on continuous variable, unlike the chi-square that it is of the categorical variables. So again, this lesson covers correlation and regression. Okay, so the scatter graph, or others call that one the scatter plot, is one of the most common graphs in statistics, but it is also the most misunderstood graph in statistics. Why? Because many others would want to see scatter plots when in fact their variables are not continuous variables. They are categorical. So it's a misconception for some or many of those who are not familiar with statistics on this scatter plot. Again, you can only show scatter plot if your data are scale data, or those are continuous. And scatter plot is used to explore the relationships between two scale variables, as I've mentioned. So here we see the relationship between how far a person runs each week and their weight. So each point represents a person. So is there a linear or non-linear pattern, as you can see? So is the relationship positive or negative? So is there an uphill or a downhill slope? Is the relationship strong? That means points are close to the line. Or weak? That means they are randomly scattered. And a scatter plot will help us answer three questions. It will also help detect any outliers, or those points or numbers which do not follow the general trend. And here, there is one outlier, someone who weighs a lot but also runs a lot. So correlation quantifies this relationship. So that is the correlation coefficient R. So the correlation coefficients range from -1 to +1, with 0 meaning there is no relationship at all. If you see that is in the middle graph, that is almost 0, so it's so scattered, the dots. And the farther away from 0 the coefficient is, the stronger the relationship. So a positive number means that as x increases, so does the y. And negative coefficients, that y decreases as the x increases. And here are some examples. So the first one shows strong positive correlation. The second one, there is no relationship. And the third, a strong negative relationship. And oftentimes, it's difficult. Okay, so there is a paper that was published stating that there was a relationship between eating the chocolate or consumption, having eaten a chocolate, and the Nobel Prize winner. So here in this paper, between the chocolate consumption of a country and the Nobel Prize winner. So what else is related to chocolate in this case? Does chocolate make you clever or crazy? Because most of the Nobel Prize winners are coming from countries which are chocolate producing countries. So somewhere in Switzerland, somewhere in Europe. So most of the most of those with having the getting the Nobel Prize winners are coming from this country. So I mean, it's somewhat also, it's funny, but is there a correlation between having or eating chocolate and making you clever or crazy? And also another one, apparently, the number of serial killers also are consuming chocolate. So this was a reply to the paper making the first claim that chocolates can make a person get that Nobel Prize winner. And there's another one, chocolates and the association between chocolates and serial killers. There are tests for correlation coefficients, but oftentimes, as I mentioned, students often misinterpret them, especially in the undergrad. So they think that a significant result means there is strong relationship when the test really tests the hypothesis that R equals 0. So you have to remember that a significant result just means that there is evidence to suggest that R is not 0. And here also, sample size plays a big part in determining what level of R is significant. So the larger the sample size, the lower the coefficient needs to be significant. And with a sample of 150, a correlation of 0.16 will be significant, and better to use Cohen's interpretation. Okay, so let us have this short exercise. So interpret the following correlation coefficients using Cohen's and explain what it means. So here are some more of the chocolate or the Nobel Prize winner related correlation coefficients to interpret. And you're going to use the Cohen's to interpret the coefficients and which ones are meaningful. Okay, so the average IQ and chocolate consumption correlation is 0.27, and by Cohen's, it is a weak positive relationship. So, the more chocolate per capita, that means also it's a higher average IQ. Another relationship, road fatalities and Nobel winners. So the correlation is 0.55. So there is strong positive correlation. So that means more accidents equals more prices. And that's funny. Sometimes, I mean, if I'm going to say this, sometimes there is statistical significance, but there is no practical significance. So sometimes the two does not go together. It is statistically significant, but practically it is not significant, like this one. Road fatalities and Nobel winners, they have strong positive correlation, which can be equated to more accidents equals more prices, but it is not practical. Does it make sense? It doesn't make sense at all. On the third relationship, gross domestic product, GDP, and Nobel winners, so correlation is 0.7. There is a strong positive relationship, so that means wealthy countries equals more prices. And this one I would believe, because for wealthy countries, they are going to support scientists. Okay, so there is funding for their scientists, so scientists could really work on their projects. Unlike here in the Philippines, it's a third world country. And support to science is not that much. I mean, the thrust of the government now is not on the support to scientific findings of how to battle COVID-19. So our ways of battling COVID-19 is not very scientific. So I would agree with this one that GDP of a country and Nobel winners have strong positive relationship. On the third hand, the last example, the mean temperature and Nobel winners. So, strong negative. So, the colder the countries, the more the prices. And it is also true because most of those getting the Nobel Prize are coming from countries which are having snow. Only that this is the first time in the Philippines that Maria Ressa won the Nobel Peace Prize. And she's not coming from the cold country. But if you take a look at records of Nobel Prize winners, most of them are coming from colder countries. Okay, so when looking into correlations, it's possible that a relationship between two variables may actually be caused by something else related to both. So there is what you call some confounding variables. In the case of chocolate consumption and Nobel Prize winners, the GDP and average temperature of a country are related to both chocolate consumption and Nobel Prize winners, and is this relationship that is being measured with the correlation. So there is a confounding variable. And what is that confounding variable? It is, in this case, it is the GDP that confounds uh, the relationship of chocolate consumption and Nobel Prize winners. Okay, so the data set being used for the following slides is a sample from a larger data. So as you can see, there are informations. Okay, so continuing information, containing information. So these are, in this case, we're looking at the measurements of the baby at birth. Okay, so such as the birth weight and the gestational age, and of their parents, the height and the weight of the mother, as well as uh, whether or not they smoked. Okay, so we're looking into the factors affecting the birth weight of babies. So what we're looking at is an SPSS sheet. Okay, so what will we do next is we're going to describe the relationship between gestational age and birth weight, and we put a line of best fit through the data so that roughly half of the points are above and below the line. So we call that line as the best fit, the line of best fit. So you can see that scatter plot. That's how it looks like in an Excel. I mean in an SPSS output. But you can put a line. You can insert a line so that it's going to divide it into two. You have the upper one and the lower one. Okay, so if you look at it, okay, so look at the concentration of the points. If you take a look at the concentration of the points, they are concentrated on that line. So that means to say that there is strong positive relationship between birth weight and the gestational age. So if the baby is not born prematurely, is the baby is of enough number of days and weeks, then the birth weight is also higher. And that relationship, if you see it, it is linear because it's somewhat concentrated on the line. Regression Okay, so if we're talking about regression, regression produces an equation for the line of best fit. Okay, so the equation can be used to predict values for the dependent variable given the independent variable. So more commonly, students use regression to look for significant relationships. The computer here classifies the line of best fit, which minimizes the sum of the squared residuals. But yeah, this one. But actually, what are residuals? When you say residuals, these are the difference between the observed and predicted weights. So again, when we say residuals, those are the difference between the observed dependent variables and the predicted value from the regression equation. And these residuals are squared and added together. Okay, so if this is your regression line, that's y equals a plus bx. If you notice, this is a slope-intercept form. Okay, so a is the slope and bx, a is the intercept and bx is the slope. B is the slope, the beta. And this here, if we're going to take a look at the difference between this line and the distance on that point, we call those as the residuals. And in the regression produces a line of this form where alpha is the intercept, as I've mentioned, and the beta is the slope. So if we relate it with the subject on analytic geometry, this is the slope-intercept form of the equation of the line. Okay, so this is how your linear equation would look like. Okay, so students may struggle with this if they do not have studied math so well. So, yeah, if they do not remember much of their analytic geometry, and they may not be interested in this either, as they are just using regression to find significant relationships, but not really on the understanding of these residuals. The hypothesis test in regression involves testing that the slope is zero. So meaning to say, if the slope is zero, then the line is horizontal. This means that every baby would be classified as of the same weight, irrelevant of what gestational age they are. So that means the slope is zero, so constant. Okay, so the weight is constant regardless of the gestational age. So if we're looking at the model, how good do you think a model with a slope of zero would fit on this data? So would you reject the null straight away? If you look at an output from the SPSS, you have your key regression table. So the first table that you're going to look into is the coefficient table. So if you notice, the constant is negative 6.66 and it is significant. Looking at the C column, it is 0.004. Okay, so, and then you have the you have also the 0.36 as the gestational age, and it is also significant. P-value is less than 0.001. So you have your equation that is negative 6.6 plus 0.36x. So the key table from the regression output in that SPSS contains the slope and the intercept of the regression line as well as the hypothesis test. So the coefficients of the line are in the column labeled beta, that is the unstandardized coefficients. And so the estimated regression equation is the one I mentioned, negative 6.66 plus 0.36x. And the slope is significant because it is less than 0.001. So if students are not interested in predicting, if you are not interested or if others are not interested in predicting using the equation, they just need to report the p-value and interpret the coefficient for the slope. That is, the weight increases by 36 pounds for each extra week of gestation. And notice that if we when we report using two decimal places. So sometimes it's not really important to look into the slope intercept form of the line, and we are going to say the slope is significant because that is very mathematical. What we're after here is on relationship between the gestational age and the weight of the baby. So you would say, again, if I'm going to repeat that, the weight increases by 36.36 pounds for each extra week gestation. That extra week gestation, that is 6.6. So you can have it 7. So 1 week additional gestation. So how reliable are predictions? Your R squared. Okay, so another important value contained in the output is the R squared. This is the measure of how well the model fits the data and therefore how reliable predictions are. So for simple linear regression, R squared is just the correlation coefficient squared. It therefore takes values between 0 and 1, and turning it into a percentage makes it easier to explain. So here, we would say that 50% of the variation in weight, in birth weight, is explained by the model including gestational age. And this is quite good for a model containing only one independent variable. And what constitutes good varies by discipline. So if we're talking here of maternal health, and that is really good. Assumptions for regression. Okay, so there are several assumptions for regression. The first is that the relationship between continuous, independent, and independent variables is linear, which is confirmed using the scatter plot. So when you confirm that, you use the scatter plot. And the second, two are available requests on SPSS. You have the plot section for the regression. So that is to assess whether the spread of residuals varies depending on the predicted values, and the second, whether the residuals are normally distributed. So you have that homozygosity. Okay, so that is the variance of the residuals about predictive responses should be the same for all predictive responses. And residuals are independently normally distributed. So if you plot the residuals in a histogram, it would look like this. That is how we are going to check normality. So there is outliers are outside. So histogram of the residuals look approximately normally distributed. So when writing up, just say normality checks were carried out on the residuals and the assumption of normality was met. You only need to say that checks were carried out. And this plot also shows predicted values on the x-axis and residuals on the y-axis. So what we want is random scatter with no patterns. So one problem to look for is an increase in the width of the scatter as predicted value increases. So there is a problem with homoscedasticity if the scatter plot is not random. So a funneling shape such as this one suggested problems. What if assumptions are not met? Okay, so here are some examples of problem data. So the histogram on the left shows residuals that are very positively skewed, and the plot on the right shows increase in variability of the residuals as predicted values increase. So the dependent variable needs to be transformed, and the most common transformation is to take the log of the dependent variable, and the analysis is you have to rerun the transformed variable and the assumptions checked again. And the downside to this is the interpretation of the output changes, and some students will struggle in the interpretation if you are using this one. Okay, so let us have that example. Okay, so investigate whether mother's pre-pregnancy weight and birth weight are associated, and then you use a scatter plot, correlation, and simple regression. So if we run that, okay, so we describe the relationship using the scatter plot and correlation coefficient. So the R is 0.39. And another important value contained in the output is the R squared. So this is a measure of how well the model fits the data and therefore how reliable predictions are. So for simple linear regression, R squared is just the correlation coefficient squared. So it therefore takes values from between 0 and 1. So turning it into percentage makes it easier to explain. Solution to that. Okay, so the Pearson correlation is 0.39. Okay, so if you're going to describe the relationship using the scatter plot and correlation coefficient, so there is moderate positive linear relationship between mother's pre-pregnancy weight and birth weight. So generally, birth weight increases as mother's weight also increases. And if you're asked to find for that regression line, so you have the pre-pregnancy birth weight p-value, so that is 0.011, and the regression equation is 3.16 plus 0.03x. So how you're going to interpret that? There is significant relationship between mother's pre-pregnancy weight and the weight of her baby. Then you're going to mention the p-value, which is 0.011. Pre-pregnancy weight has positive effect or effect on baby's weight with an increase of 0.03 pounds for each extra pound of a mother's weight. So if mother is going to grow heavier, an increase in an extra pound weight increase of the mother, there is also a corresponding 0.03 pounds increase on the baby's weight. So if we check assumptions, linear relationship, okay, so that's it, how it looks like.